Okay, welcome everyone to the DeepChem meetup. We are really excited to have you here. So for those of you who may know about us, DeepChem is an open source project that does a lot of cool things. Today we'll have a number of presentations about DeepChem. I'll start us off with a brief just introduction to DeepChem for a few minutes. Then we'll have our three talented Google Summer of Code interns for the summer present on their work. And finally, we'll have a presentation from an ongoing research project, ChemBERTa 2, that is a collaboration between DeepChem and a number of other organizations. So with that, let me just go ahead and turn on my full screen mode. One sec. All right, to keep things simple, I'm just going to present like this. Could one of the speakers confirm that you're able to see my presentation slides?
Yes, it's visible for me.
Okay, wonderful. So first, welcome. I'm really excited to have you here. We used to do DeepChem meetups in person several years ago in kind of near Stanford University where the project was started. Since then with the pandemic and other things, we've had a long hiatus, but now we're back with a new online format. So DeepChem's been in the intervening years continually developed. We have a very broad user base of kind of organizations that have used DeepChem. So every organization listed on the screen has actually written a research paper using DeepChem. So as you can tell, we've had a pretty broad impact on the industry and the academic ecosystem as a whole. And we continue to grow as an open source community. So we have over 3,000 stars on GitHub. There's over 50 downstream packages that depend on DeepChem and over 100 contributors. We've had 15 releases so far, and our 16th release is just about ready to come out the door. So stay tuned. Today, we'll have a number of really interesting talks, and I think to provide just a little bit of context for those of you who might be new to DeepChem, the goal behind the project is really to provide tooling for scientific AI applications. We primarily have focused on molecular machine learning, and we provided a number of tools for loading data sets, featurizing them, that is transforming them into a format suitable for machine learning, storing the data sets, splitting them in different ways, transforming them, doing downstream models. And sorry, I apologize, I'm still kind of letting people in from the waiting room right there. So my apologies for the beeps you're hearing in the background. And deploying these models for production. In the past, we've primarily focused on molecular machine learning applications, but increasingly our vision of where we see the community going is that we'd like to make DeepChem into a broader framework for AI-powered science. This means including new tools for dataset generation, such as simulations, some of which might be powered by deep learning models in their own rights, new models. So we have a widely viewed model wish list of over 30 new models in scientific machine learning that we're looking at to the community. We have some new contributors helping us add on some of these models. We're looking to improve our modularity, so you can use DeepChem as a building block in a broader ecosystem infrastructure. And we're looking to add many new data sets. We're also looking to grow support for our non-molecular applications. And you'll actually hear a little bit about some of this work later today from some of our speakers. So we're looking to grow support for materials modeling, proteins, partial differential equations, and many more scientific applications. Our broad goal is to create an open source community for applying AI to scientific applications. So if you're working on a model that's related to AI and science, we'd love to work with you and help you maintain and extend your code base. So we hope that after you listen to today's talks, you'll be excited and come join in on our weekly developer calls, which are open to everyone in the public, and to become a member of our community. With that, let me just turn over to our first speaker, Atreya. So Atreya, let me go ahead and just hand the screen over to you. So go ahead and please grab the screen.
Thank you. I'll just start presenting now. Give me a minute. Please let me know if my presentation is visible. I will start as soon as it is.
Yep, go ahead.
Great. So Hello and welcome everybody. I am Atreya Majumdar and I'm an electrical engineering student from India. So this summer I was working as a GSOC student with DeepChem, and my project was adding the molecular tension transformer to DeepChem. So to begin with, what is the molecular tension transformer, or MAT? So MAT is an improvement on conventional transformer architectures. So MAT actually adds interatomic distances and the molecular graph structure to the transformer architecture. Now, as it is based on transformers, MAT utilizes multi-headed attention for its attention module. So why did I choose MAT and why did I want to integrate this into DeepChem? So DeepChem required a few sequential models for molecular tasks, and MAT actually performs quite well on different molecular prediction tasks. Now, due to MAT's self-supervised pre-training, it is pretty easy to tune and maintain as well. And last but not the least, the weights that you get from MAT are actually chemically interpretable, which can be quite beneficial. So coming to the architecture, this is just a small diagram of the architecture that you can find in the original base MAT paper as well. I'll be going over the implementation details in the following slides. So coming to the implementation details, we'll first look into how we pre-process our input data. So first we have a batch of SMILES strings, right? So each of these strings represents a different molecule. Now, these are the molecules that we will be working with. So these molecules are passed to something called the MAT featurizer, which is a featurizer which pre-processes the given SMILES strings. So the MAT featurizer will actually resolve the given SMILES string into a MAT encoding data class instance. Now, what is MAT encoding? MAT encoding is a custom data class that I have defined for the purpose of being used in MAT. So as you can see, MAT encoding encompasses three different matrices. So the first one is the node features matrix, which defines the features of a node. Then we have the adjacency matrix, which defines the adjacency of different atoms in the molecular graph. And then finally, we have the distance matrix, which defines the interatomic distances in the molecule. Now, the code for the MAT featurizer can be found on GitHub in the feed section of DeepChem. And it's also linked here in case the presentations will be made available to the public. Now, moving on, what dataset have I used? So for the current implementation of MAT, I have implemented it as a regression model. And the dataset that I have used is the free solve hydration enthalpy dataset. So the dataset actually just contains two columns. The first column is SMILES strings, and the second column just contains the hydration enthalpy values for every corresponding SMILES string. So again, the code is there in DeepChem. Now, this has been added to MoleculeNet. And we will be adding classification functionality to DeepChem, so to MAT soon. So the MAT implementation basically, so how does it work? So once we get a batch of processed molecules, which is a batch of MAT encodings, we feed this to MAT model. Now, MAT model is basically the architecture for MAT, which is made with custom layers, and we'll be going over these layers in the following slides. So the MAT model class actually derives from the torch model base class, which is defined in DeepChem. And this class invokes the MAT class, which in turn derives from nn.module. Now, the forward call for MAT is simply a wrapper function which defines an encoder block. Now, this encoder block is made using the layers that we have defined specifically for MAT, and I will be going over them in the next slide. So in DeepChem, MAT utilizes 6 crucial layers. We have implemented these custom layers by looking at the base research paper. So the first layer is the MAT embedding layer. Now, the MAT embedding layer just takes input and computes a vector representation. So you basically pass a MAT encoding to it, and then it will compute a corresponding vector representation. Next, you have the multi-headed MAT attention layer. Now, this layer is the primary multi-headed attention module for MAT. Next, we have sublayer connection. Sublayer connection is simply just defines residual connections in MAT. Then position-wise feed-forward defines the position-wise feed-forward or FFN algorithm for MAT. Then MAT encoder layer just wraps the previous three layers, which are multi-headed MAT attention, sublayer connection, and position-wise feed-forward, into one single layer. Now, multiple MAT encoder layers can actually be stacked in order to form an encoder block. Then, last but not the least, we have MAT generator. So MAT generator defines the linear and softmax generator steps for MAT, and the output from the encoder block is fed to the generator, which computes the final answer. So this is a basic introduction to the work that I've done, and now I'll be going over a tutorial that I've made in order to help everyone understand how to implement it with code. So please just give me a minute. I'll pull up the notebook. I'll just share a window, and there we go. Please do let me know as soon as my notebook is visible.
Yep, you're all good.
Okay, great. So this is a basic tutorial. So the introduction part is what I just talked about, that MAT, or the molecular attention transformer, is a model based on transformers aimed towards performing molecular prediction tasks. And it's easy to tune and performs quite well relative to other molecular prediction tasks. Now, the weights from MAT, as I mentioned earlier, are chemically interpretable, thus making the model quite useful. I have referenced the original paper here as well. So let's go over the code, right? So to set up, you can just, could you increase your font size a bit? Sure. Is this okay?
I think no,
all right.
Go ahead.
Great. Yes. All right. So this is the basic setup. So here we're just getting everything ready for and installing stuff. And then here we're just installing pre-DeepChem. Then we'll be importing required modules. So we're just importing DeepChem, we're importing MAT model, MAT featureizer. Because we're importing MAT featureizer separately, because I do have an example in the notebook to show how MAT featureizer itself works. And then plot is just imported in order to plot the losses. So coming to the MAT featureizer, you will just have like an array of smile strings, right? So that is a batch of smiles strings. So you have this, and then you just pass it to the MAT featureizer. You can call it using dc.feed.mat featureizer. Now output will just be featureizer.featureize smile string, and then what you get is an array of MAT encodings. Now, since we only passed one smile string, it's a one element array, right? The smile string array. So our output will be an array of MAT encodings where there's only one element. So output of 0 will define that element, and type is, as you can see, MAT encoding. And there are three different matrices in it, as I mentioned earlier: node features, adjacency matrix, and distance matrix. And you can call it using object.node_features, object.adjacency matrix, and so on. So here I've just printed the three matrices, and that's how it goes. Now coming to the data set, how do you call the data set? You can just call it like any other molecule net data set, dc.molnet.load, and then data set. So here we've just done a train test validation split, and then the IDs are basically just which molecules are there. And then I'm just printing like what train data set is. So it becomes a disk data set, which if you're not familiar with, it's a data set type which is defined in DeepChem. It's in the utils part if you'd like to go over it. Then coming to the main crux of the tutorial, training the model. So I do not have a GPU available, which is why I'm using device equal to CPU. But if you do have a GPU available, then you can set device equal to your corresponding GPU. And then you just initialize the model using model is equal to MAT model. Or if you have an imported MAT model, then you can do dc.models.torch_models.mat model. Now I'm just initializing losses and val losses as empty arrays so that I can keep appending my loss values to them. And here I'm just training. So I'm actually just training for 10 epochs because, as I mentioned, I don't have a GPU, and MAT is actually slightly computationally expensive to train. So it was taking quite a long time for me. So I just trained it for 10 epochs. Although if it is highly recommended that you use a GPU and you train it for like a few hundred epochs at the very least. So this is just a normal training loop that we've written, like how we train all of the DeepChem models. And you can ignore these warnings. These are not relevant to do what we're doing here. So here we're just plotting, that's a graph, and then coming to testing the model. So we'll just be using predict on batch in order to test the model. So here for predict on batch, if you remember, output is basically the molecule and the process molecule that we used for seeing how the matte featurizer works, which is basically from here, right? So coming back to testing the model. Sorry, just 1 second. Yeah. So I'll just do model.predict on batch output, which is basically a batch of matte encodings, and it's a single element array. So then you get an array of just one prediction because there was just one molecule there. And this is the predicted hydration enthalpy for the given molecule, which was CCC. So that about concludes my presentation. And if there are any questions, I would love to answer them.
Okay, thank you, Atreya. If for anyone in the audience who has a question, if you could write them in the chat, then I will call on you.
Sure, thank you, sounds good.
Okay, awesome. So the floor is open. So if you have any questions, please type them in. So I'll start us off kind of in the meanwhile. So maybe just as a quick question for you, Atreya, how would you compare MAT with other types of graph convolutional models like the GraphCon or Weave that people have been using? What would you kind of say is the similarities or differences there?
Similarities or differences. So this is here, it's just that our input is a molecular graph, right? Like that's the only thing. Otherwise, it's just a normal transformer model. So that's about it, I guess.
Yep, I think so. It looks like we now have an external question. So Andrew, do you want to go ahead and read your question?
How does the predicted enthalpy compare to the experimentally derived value? So as I mentioned, I wasn't able to train the model for very long due to computational constraints. But otherwise, looking at the base paper, which I have followed quite religiously, the model does outperform most other models which are tasked with molecular prediction tasks. So that's there. So if you're able to train this, I'm sure it'll perform quite well. In line with what the MAT authors showed.
Great, thank you.
Thank you.
And just to briefly kind of jump in and mention, so we are working towards a new MoleculeNet paper. So MoleculeNet, for those of you who haven't heard of it, is our benchmark suite. So we'll hope to add MAT to the MoleculeNet 2 benchmark suite, but we haven't yet updated our results there. So I've added the repo for anyone who's curious. Are there any more questions for Atreya? Okay, so going once, going twice. Okay, great. Thank you, Atreya. And if anyone thinks of a question, we can come back at the end. So we'll have some time left over for questions at the end. So just type your questions here and just note that it's for Atreya. And now we'll kind of move over to our next speaker, Ashwin. So let me go ahead, Ashwin, would you still like me to go ahead and share the screen to...
Okay, so I thought I'd go ahead with the presentation. If there are problems, then we could switch over. Well, do you think that's good?
I think that sounds good. In case you have network issues, we can swap to my presentation, but please go for it.
Awesome. All right. Just give me a moment. Please let me know if the tab is visible. Hello?
Yep, can see it. Go ahead.
All right. So, hey, everybody. I'm Ashwin. I was a GSOC student with DeepChem this summer, and I had worked with DeepChem to bring retrosynthesis models to make reaction predictions and so on. To start off with, I'll talk about why retrosynthesis is important. So what retrosynthesis does is it just gives synthetic chemists a systematic and a structured approach to plan their synthesis. And organic synthesis really is at the heart of chemistry, and it has a wide range of applications. Some of which I've listed on the screen, like for drug design, pharmaceuticals, biopolymers, and so on. And really making these molecules, all of these molecules are really complicated in structure, and to make them in a very efficient way requires very careful planning. And this is where retrosynthesis comes in that it gives synthetic chemists a very nice way to build up their molecules. So I'll talk a bit about what retrosynthesis actually is. So the main idea with retrosynthesis is to just break down your target molecule into smaller and smaller chunks so that you eventually start off with readily available precursors. So the idea is to just make the right disconnections. And the thing with this is that you need really large information, knowledge of chemical reactions to make these disconnections, because not every disconnection that you make is going to be chemically valid or useful. So the way synthetic chemists actually do this is through having a very strong chemical intuition. They gain this over studying a lot of reactions and over a long period of time. And this inherently causes a problem when we try to teach this to something like a machine, because the space of possible chemical reactions is just huge. You parameters or a lot of different reactions to make the right disconnection. So how do we actually attempt to solve this problem? So one easy solution that has been proposed many times in the past in literature is to treat this problem as a machine translation task, as a sequence-to-sequence translation task. The way in which you see a reaction is just as a translation from the reactants to the products. And by translation, what actually is getting translated is the Smil's representation. Is you sort of convert from the reactants Smile string to the product Smile string. So it becomes a seek-to-seek task essentially. So I'll give you an example of how we would go about something like this. So at the top, the really long string that you see at the top of the red arrow is an example of reaction smiles. And the reaction smile just has smiles encoding for the reactants, the reagents, and the products. And below the arrow, you can see the same reaction, but represented in a more the conventional, more familiar format of the molecule. And what we want the model to learn is to just the sequence-to-sequence translation from the source smiles to the target smiles, the source being the reactants and the reagents, and the target being the products. And retrosynthesis is essentially just going from the target to the source. You do a disconnection to get back both of these molecules. Now, how we do this with DeepChem is we first have to actually get in all of these reaction data sets. So for this, we had added support for the USPTO dataset. The USPTO is the US Patents Office dataset, which has over 1 million reactions. It is the standard for training reaction prediction or retrosynthesis models. In DeepChem, we have added support for even loading different subsets of the USPTO dataset. Since the dataset is so big, we've added support to load in different specific splits, like the USPTO 50K, USPTO MIT, and the USPTO stereo. All of them have their own special characteristics. Like the USPTO stereo, for example, has more reactions where the molecules have stereochemical information. So all of these have a different number of reactions, and they're used for specific tasks. And sometimes you use 50K when you want to train a small scale model or when you're fine tuning, and so on. So moving on. So now that we have the reaction data set, which is just a bunch of smile strings or the reaction smile strings, what we want to do is actually convert these smile strings into things that the model can actually digest. This is where we brought in the reaction tokenizer. So the reaction tokenizer is just a wrapper over Hugging Face tokenizers, which the idea being that we basically want to convert the smile string into something that the to use the robot featureizer in the backend. The robot featureizer was tailed using the smile tokenizer, which was done in DeepChem previously, and theoretically the reaction featureizer can actually use any pre-trained Hugging Face tokenizer as long as it was trained on molecules, basically on smiles. So this really is the general idea of this project, is to bring in a whole variety of models that you can use to do the same task. And another feature of the tokenizer is that it supports mixed training, which means that you can actually mix the reactants and the reagents or have them separated. Now, what this does is that it actually makes it harder for the model, because it basically causes the model to predict the reacting centers from a larger set of possibilities. So I'll give you an example of how the tokenizer works. So when you have the input smile string, the tokenizer just converts the source, which is the reactants and the reagents, into just a bunch of NumPy lists with NumPy arrays with the corresponding input IDs and their attention masks. The robot model takes in, and this is what we would be using for our purposes. Now, coming to the actual model, so the model that we have proposed is very similar to previous work on the molecular transformer. So what we have is basically a ChemBERTa backend on an encoder-decoder model. So the encoder-decoder model is Hugging Face's implementation of using pre-trained weights to train a transformer. So in our case, we use warm-started ChemBERTa weights to basically to use them as weights for the encoder and decoder, and we use this to make the retrosynthesis predictions. Unfortunately, the model wrappers are not yet on DeepChem; they're still work in progress. But this is the general flow of how you would do a single prediction on a molecule. So it starts off with the molecule with its reaction smiles format. It's then passed to the robot tokenizer, which converts it into the three embeddings, which is the input IDs, the attention masks, and the labels, which pass on to the ChemBERTa encoder, which converts it to the embeddings and passes it to the decoder. All of this is handled by the Hugging Face wrapper, which eventually decodes and gives you the corresponding targets, that also corresponding source molecules that you would use to build up the target molecule that you'd want. So some future improvements that we could make are that presently the model only supports a single-step disconnection, which basically means that it can only make one disconnection at a time. Now, for practical purposes, this may not be what we want, because when we have a really complicated molecule, we might want to make multiple successive disconnections. And presently, the way in which the model is proposed, it will not be capable of doing that. And we'd have to figure out a way to make that work. Another possible improvement is that basically there are other methods cropping up in the literature, like using contrastive learning or graph-based methods that perform quite well compared to the transformer model. So we might also consider adding these models so that the DeepChem support for retrosynthesis is more enhanced. So yeah, that's about it for my presentation. I have a short tutorial on how you would create these how you use the tokenizers to create the featureized data sets, and I'll present that shortly.
And if you have any questions, feel free to start typing them in on the side, and Ashwin will address them at the end. And I think, Ashwin, most of your presentation came through. I think it cut in and out, but just like half a sentence here and there. So if anyone has any questions about things that were cut out, leave a question here and we can hit them in the Q&A.
All right. Please let me know if it's visible. I'll get started.
Yep, it is visible. Go for it.
All right. Okay. So the notebook is also unfortunately not yet in the official DeepChem examples, but this is the latest version. So to start off with, we just do the usual way of installing DeepChem on a local environment. We just install DeepChem. And one thing to note is that since we use the Hugging Face backend, we want to install the Transformers library. And once we have that done, we just move on and we import DeepChem. We import the Roberta tokenizer. Since the reaction featureizer uses the Roberta tokenizer in its backend, we want to import that. So to start off with, we load in the USPTO datasets, and the way we do this is very similar to how you would load in any other molecule net dataset. Just call in the corresponding loader method. In this case, it's the load USPTO, and then you pass in. Additionally, you can pass in the subset that you wanted. Like I mentioned earlier, you could pass in full if you want to load in the entire dataset. If you want to load in just the MIT dataset, you could just pass in MIT as a string. And you could use a different split for your train. All of the dataset loading infrastructure that is there on a standard molecule net dataset is also supported here. So that is there. And you can also separate the reagents for the mixed training. That is also possible using the toggle there at the end. Once that's done, once the dataset is loaded, we just separate them into the corresponding train, test, and validation splits. And I've just printed out an example of a training dataset, of a particular example from the training dataset. The first list shows the input IDs and attention masks of the reagents and the reactants, and the second list shows the products encoding. After that, now this part is where you actually call the model. This is similar to how you do it from the Transformers library. You just call in the model from their encoder decoder infrastructure. You just construct it using the ChemBERTa weights as it's shown here. We use the same ChemBERTa weights for the encoder and the decoder, and that's how you construct the model. Unfortunately, the training steps aren't complete yet, but the way you train is very similar to this. You just pass in the dataset to the sequence-to-sequence trainer, and it would do the training. And like I said earlier, this part is still work in progress, but this is how you would do it to get the model up and running. That's about it from my end. Please let me know if you guys have any questions.
Okay, great. Thank you, Ashwin. So it looks like we have a first question from Seyone. Seyone, do you want to go ahead and read your question out loud if you're there?
Yeah, sure. I guess my question is, do you think if you pre-train the language model on a similar chemical library to USPTO instead of PubChem, the model might perform better? What are your thoughts on some ways to boost some of the benchmarks?
Oh, that's a good question. I think what I think is that it's very likely that the model would do better if it was trained on the USPTO datasets, simply because there might be some molecules that are not there on the PubChem dataset but are there on USPTO. Although PubChem is a really good standard, and the tokenizers and stuff which are trained already trained already work quite well, but it's very likely that when it's trained on the USPTO, it would perform better. Since we are also going to be predicting on reactions from the subset of the USPTO datasets. So I expect it to do better because we also have the disconnections related to the same examples which are there on the dataset. So yeah.
Thanks.
Awesome. And maybe as a question that I have from my end, what would be the steps required to take your current implementation, Ashwin, and turn it into an actual retrosynthetic engine that could be used by practicing chemists? What are the things that would need to be added?
Oh yeah, like I said in the presentation, the main thing that is lacking is, of course, apart from the model, is that we want the model to make multiple disconnections. There are many approaches taken in literature to handle this issue, and this I think is I think the key drawback that we'd have to handle, because it really is the most important step that we need to actually make this a practical tool. We basically want to make sure that we get in the multi-step disconnections done correctly. That would enable this as a tool for making retrosynthesis predictions.
Okay, awesome. So last call to anyone here for questions. And in the meanwhile, Vignesh, if you could go ahead and start setting up. But last call for questions for Ashwin while Vignesh is setting up. And maybe I have just one more question here as well. Like, could you comment on some of the other like retrosynthetic models in the literature, like, and how they compare to this more NLP-based approach?
So presently, the graph-based models, I think the graph-to-graph translation approach is doing quite well. I am not actually entirely aware of what is the best model right now, but it is. As far as I can tell, it's not the molecular transformer model that we were implement in this case. I think the one by Vignesh's team, I think it was the graph-to-graph model that does really well. But yeah, we will have to see. And there are, as I mentioned, there are some approaches taken based on contrastive learning. Those do really well as well. So there are a lot of other examples. I think like the team at IBM Research for Philippe Charlotte, they were working on this problem, and they're doing really good work on this area.
Okay, awesome. Thank you, Ashwin. Vignesh, do you want to go ahead and grab the screen?
Yeah, sure. I'll start. Just give me a moment. Is my screen visible?
Still waiting. Oh, it's coming up.
Okay, great.
Go ahead.
Hello, everyone. I'm going to be giving a presentation on differentiable physics with JAX in DeepChem. My name is Vignesh, and I'm a senior at IIT Roorkee, currently majoring in physics. Over the summer, I had participated in GSOC as a student developer with DeepChem, where I had worked on adding JAX support and implemented a pins model API. So let me start my presentation by introducing JAX. First, JAX is a mathematical library supporting array manipulations similar to NumPy. Along with it, it also supports automatic differentiation in CPUs, GPUs, and TPUs, which are suitable for high-performance ML research. It's been gaining a lot of popularity, and we at DeepChem wanted to explore its benefits in the molecular ML community. Some of the popular projects are the JAX Molecular Dynamics project and the AlphaFold for protein folding problem. To build, DeepChem supports PyTorch and TensorFlow backend using Torch and Keras model API. We wanted to introduce JAX model API, with which one could build JAX-based models in DeepChem. On the right, I've listed out some of the benefits of JAX, and here are some of them. First is that it uses a purely functional API, which makes writing machine learning code similar to mathematical functions. It follows a declarative style, and some of the other common benefits which are suitable for machine learning are it supports automatic differentiation, vectorization, JIT compilation, which speeds up your training, and it's quite easy to train models on multiple GPUs and TPUs. These last three steps are provided with these set of functions called transformations in JAX. Okay. So I'll just list out like JAX is quite similar. JAX is very similar to NumPy, and in fact, it gives out its own NumPy module called JAX.NumPy, as you can see here. In order to avoid confusion, I'll be referring to the original NumPy as NP and the JAX NumPy as JNP. You can perform operations interchangeably with NumPy and JAX arrays. As you can see here, that I've defined a NumPy array and a JAX NumPy array, and I've computed a dot product, and it would work pretty smoothly. Another important thing is that I'll define what a gradient is. So in one dimension, it is the change in value with one variable with respect to the other, which is often called as the slope. And when you come to multiple dimensions, you kind of take it with like set of parameters in different directions. So in order to we write in JAX, we write pure functions for whose gradient we want to calculate. So we can see that we have defined a square function here, which calculates the square of the given variable. So if we, and you can see that it's a pure function, it does not change any global state or anything. So if we have an array that's given to you that's x small, defined at 3, if we want to compute that, we want to calculate, we want a function that computes the derivative of this function, we use the JAX grad function, which composes it with the original pure function and returns a function which acts as like the derivative of the function. So when we pass in the square, the original function with the original variable, we would get an output of 9. And when we pass it with the derivative function, which was taken with the grad, it would return 6. If you have multiple arguments, you can usually pass it with the arguments. It's not a it's quite easy. That's given in the document. If you want to compute higher order derivatives, you can compose them using multiple grad functions. For example, if you want to calculate the second derivative of a function, you can use it with you can nest it with 2 grad functions. So that would probably return a 2. And if you want to learn more about like other higher order differential, other complex derivative operations like the Hessians, Jacobians, forward and reverse Jacobians, you could check out this link. I'll also go over what a neural network is. So usually a neural network has 3 layers: the input layer, where you feed your data, and the output layer, where we represent as a function of the input data, and then we have the hidden layer, which has the weights and the instructions with which the weights need to act on the previous layer. Each layer is usually defined by by a linear multiplication operator followed by a non-linear function, and when you stack them up, we usually get a function that represents the entire function. So if x is the input value, a neural network can be thought of as like a function that acts on this input layer and returns an f of x. So we usually use this like as a universal approximator. I'll go over this a little later. So we will be using the HiQ module for building our neural networks. We will represent a neural network as a function of its weights and input as parameter, and here are the operations performed on it. So due to this pure functional style of JAX, let's define it. Let's define it using the HiQ module, where I've made a multi-layer perceptron function that has 2 layers. The first layer with 256 neurons and second layer 120 neurons. That is kind of represented here. You just have a one cross one variable vector, and it goes into the neural network with 256 and 128 neurons, and then you have a final scalar value output. So this val can be thought of as the f of x that I was referring over here. That is a function of this x. And one more thing which you need to know is that in HiQ module, you need to know that like if you're coming from a PyTorch or a TensorFlow backend, you usually have your neural networks defined in a class structure, where the class already has its weights and it performs everything in the backend. But with HiQ, you have the control of the params. So usually a neural network is like a function of the parameters and the input, and there is a function which kind of does the multiplication operators with the parameters and the input layers. So here you kind of have the params is like a dictionary of all the weights inside the neural networks, and the forward function kind of tells you that what kind of operations you want to do with the params. So, for example, you could either have a forward layer or a convolution layer or a sequence layer, your wish. So I'll just walk through like a tutorial notebook to keep it to help in understanding. So we have this here is the setup, and here are some of the important libraries for this tutorial. And here I've defined a neural network that's same as the code that I showed in the slides, where we have defined a normal perceptron layer, 2 layers, and here we're trying to solve. So now let me talk about what a differential equation is. So a differential equation states how a rate of change in one variable is related to another variable. So if I define 2 variables, one is the position that's defined by x, and the other is velocity that's defined by dx by dt. We often refer it as x dash. Uh, then in order to simulate the position of a spring motions, physicists and mathematicians kind of observe that it can be modeled using an underlying data, which can be modeled using a differential equation that is kind of represented here. The change in velocity is proportional to the position coordinate. When you expand this as following this equation, you would have that it's the second derivative of position with respect to time is proportional to the position coordinate. And we solve this differential equation, we kind of get this result where the x of t gets the solution, and you can actually simulate the results here. So sort of like kind of following his underlying rules, you can kind of simulate real world instances. But here we have simulated the position of the spring using this the green line over here. It shows the position, and the red line indicates the velocity. Okay. So now I'll start by introducing. Before introducing pins, I'll just give a small problem statement. Like, imagine we are in like we have a physical system with us, where we have 10 random points about the physical system between the range of -2 pi to 2 pi. And we also know that this physical system follows this one underlying rule, and it is modeled by this differential equation that the derivative of the function with respect to x is equal to minus sine x. So if you want to just take a look over it, so here is the range minus 2 pi to 2 pi, and here are the data set, and here we have modeled that here are these 10 random physical data that we have observed. And you can see that it kind of follows this W shape if you walk over it. And if you already know how to solve simple differential equations, then when you solve this differential equation, you would know that this equation is f of x is equal to cos x between this range. And you can see that the physical data kind of satisfies with the actual data. The violet line indicates the cosine curve between the range of minus 2 pi to 2 pi. And I've added a little noise to the physical data because in order to simulate a real life I've added noise to the data to simulate real world observations. So just walking over it in the code. So here, so in given and in out given are the data that we are given with us, where we are taking a range between -2 pi to 2 pi, and we're just taking 10 random points, and we are trying to simulate it over here. And also, yeah, the random noise is given over here. So, and here is like the test data where that shows that within the range what the actual data is supposed to follow. So the violet data is the cosine curve that it's supposed to follow, and here are the little bit of noises given here and there. So if we were to solve it using just like as a supervised task, using just neural networks, what we would do is you take this column as the input layer, f of x as the output layer, and pass it through a neural network and train your model on it. So if we did that, that's kind of represented in this flowchart here. You have the input layer x, you pass it through your neural networks, you have the value, and you have the original data, and you pass it through like something like a loss, like a mean square error loss, and then you take the gradients of it and you give it as a feedback. And once you train the data, you can see that the model has kind of learned to overfit the physical data, and you do know that the physical data has like these physical observational errors, and has still managed to follow them. And apart from that, it is kind of diverged once we cross the boundary points of the physical data. But is there anything we can do better? We also have knowledge about the underlying rule of the system. So this is where we can use pins as like a model. So we are going to be using pins as like a regularizer. So the original equation, okay, and I'll just show it. I'll just show this operation of the neural networks in the Colab notebook as well. So here we have used the JAX model API to train the model. And this is like the code. Here I've defined the data set, and here's the JAX model and your fit function. And when you train the model, you kind of have this, you kind of get this resultant curve. You can see that the model has kind of diverged at the ends, but let's see if we can do something better than that using pins. So here, so this is the underlying rule that we know about the system. Is there a way we can incorporate it into this? So, like I had mentioned, that we kind of use this val as a neural network approximator. So this val can be thought of as the f of x that we had earlier discussed, that neural networks can be thought of as a function approximator. So here we are going to be using differential equation. So as a regularizer loss, so the val can be thought of. So till this stage, it's similar to what we have discussed earlier. So the val is the f of x. Let's compute the gradient with respect to x for the function, and let's also take the sign of that value with the value x, and compute the differentiable loss. Combining this differentiable loss with the supervised loss that we already have over here, we kind of sum it up, or any ratio weights, and then give that as a feedback to our network. Here are the improved results, where you can see that the model has kind of learned to train your model even when there is no data given here in the other boundary conditions. We had kind of defined the model till like uh, around six, that's coming to around 6.28. So we were able to train the model to out beyond the range of the physical data, and this is where pins can have their advantages. So it is used in situations where you have a very little data about your experimental system, but you also know that an underlying rule the physical system follows, and you can use that to train your neural network. And we also make sure, and it's useful only when you have the underlying data given in the form of a differential equations. So let's just walk over this in the code. So okay, so we will be using the pins model API. So we are trying to build a framework to solve differential equations. So every differential equation is different. So we kind of need to tell our model that how you're going to be what is the exact differential equation. So the pin model requires two functions. One is the create eval function. The other is the gradient functions. This is pretty trivial. I'm not going to discuss this. So the create gradient function. So first, there are two things which we need to know about the function. So first is that we need to calculate this loss as well as this loss. So the boundary data is usually for calculating the supervised loss of the function that can be visible over here, where we just use a normal supervised function. And when we want to calculate the differentiable loss, so here we are going to be taking the gradient of the neural network with respect to the params, and we are returning the differential equation. And here is the final loss of the function. And here it is. So when we train the model using the pins model API, we get our results, and you can see that it follows a more accurate curve, and it follows the actual rule of the cosines curve. And if we do a comparison between the model that was trained with just vanilla neural networks and with the pins model, you can see that there's like a lot much difference over here, where the vanilla model kind of diverges towards the end, but the pin model follows the rules given. Um, And last, if you want to see a more non-trivial example, then you could check out this tutorial in DeepChem following this link here, where we've solved the Berger's equation. If you want to learn more about Jack's official, I've added a few resources which might help you in for more resources. And if you can find the presentation in this PR in DeepChem. Thank you.
Okay, great. Thank you, Vignesh. I just speaking for myself, I really enjoyed the kind of tutorial on basic differential equations and how to tie them back to pins. And it looks like we have a first question. So over to Stelios.
Hello. So great presentation, and this is really exciting and can, the problem with a lot of these vanilla ANN models are that they interpolate well, but when you ask them to extrapolate, they are horrible. And when you're trying to do optimal design tasks, most of the time you end up extrapolating. So this is annoying. So it's good to constrain your ANN models with physics if you know the laws of physics in order to help them extrapolate more. And you do this here by applying an extra term. So you are minimizing your observation error and also your gradient error, which makes sense. But my question is, if you already know the PDE that governs the system, right, then why go ahead and find the best weights of a neural network that approximates it optimization problem, instead of just finding what are the parameters of my PDE that best match my data?
I'm sorry, I couldn't hear you. Could you just come back to the last 10 seconds?
Oh, sure.
You said last 20, 15, 20 seconds.
Sure. So the way you're going about solving this problem now is that you're trying to find the weights of a typical multi-layer perceptron, so as it fits your observations and the gradients as predicted by the partial differential equation that you know, right?
Yep.
So if you already know the partial differential equation, then why not exchange that optimization problem with the following? Find the parameters of my partial differential equation that fit my data. Right, so find the alpha in front of the cosine in this case, in your simple example.
Are you asked? Is your question why aren't we? If we have the differential equation already with us, so why do we even need a neural network? Is that your question? I'm sorry.
Oh yeah. So the question is, if we have the partial differential equation, right? Or I mean the traditional. I'm coming from a kind of computational fluid dynamics background, doing things like this in aircraft design. And the traditional approach for this is, if you know the partial differential equations that govern your system, and in fluid dynamics, that's the Navier-Stokes equations, then, and you have a bunch of data, what you're usually doing is you're trying to find the parameters, viscosity and et cetera, and a bunch of other things that match your data, and by default, always agree with the gradients that are defined by your partial differential, because that's part of the model, right?
Yeah. I think we could do that. I'm sorry, when you said parameters, you meant viscosity. I was thinking something like the neural network weight as parameters.
They're both, right? So it's here you're replacing the parameters of the partial differential equation with the parameters of a neural network. They're doing pretty much the same thing, right?
Okay, yeah. So you're kind of giving a meanings to the weights here, but for usual differential, it's sort of I'm using sort of a black box, but you're kind of giving meaning to the weights by calling it viscosity, something like that, right?
So for example, here, if let's say that it's sine 10x in your partial differential equation, but you don't know the 10, right? And you can learn that 10 directly from your data, so you don't even need the neural network in front. You just fit your differential equation directly.
So perhaps if I could just hop in really quickly, and Vignesh, feel free to kind of jump in as well if you have kind of an alternate answer. I think so. Serious. I think one of the really interesting things I think in this line of work is that you can solve dramatically higher dimensional differential equations using some of the new techniques that are coming about. So there's this really neat paper I think from Waynon's group where it's something like solving high dimensional PDEs with neural nets, or they solve something like 500 dimensional Black-Scholes equations. Using variants of these techniques, not precisely the techniques here. So I'd say I think your question is really good. Like, why not just do classical parameter estimation? And I think the reason is that the neural networks provide a new substrate, essentially for higher dimensional inference. So maybe that's like, at least that's my understanding, but I'm also just learning about this field, so I could be misrepresenting something. Vignesh, do you think that seems like
Yeah, I mean, yeah, even I actually think it's similar. Like it's sort of like, I think not every different, you don't have, yeah, I don't think we have like a general solution to all differential equations. I think that is why computational methods were also introduced. I think maybe pins are like a way of solving, like a new way of solving differential equations. Sort of like here we have taken a trivial example of sine, but if we could always go to more complicated problems, like maybe you could try checking out the Burgers equation, and there were examples of the Schrodinger's equations as well. But to be honest, even I'm learning about this field, and I would love to know more about this as well.
Yeah, and it's like, at least from my side, this becomes like extremely fascinating when if this can help you find things that you were not able to find before, and it has that potential, right? Because if you're just finding your parameters, you didn't find any new physics, but maybe then your data, your physics cannot fit the data, so there's something else going on there. So approaches like this can help you, actually find new and interesting physics into your problems.
Yeah, that's true. Yeah.
I've just dropped a link to the paper I mentioned, which I think it's a little dense, but I think that for me at least, it really I was like, oh, I get it. Why this line of work is actually super interesting, because you can it opens out this world of solving like very high dimensional PTs that just was never really on the table before. But yeah, this is all. I think, as you say, like Celius, this is all kind of very early stage work. It's like. I think Vignesh has done amazing work this summer, kind of extending it to like small classes of equations and make it general API. But yeah, this is quite far, I'd say, from being able to solve, industrial strength PDEs. But this could be. I'm really excited, and I think as a meta comment, I think that DeepChem as a community, we're kind of evolving quite a bit in that we're extending broadly into scientific disciplines outside molecules, which I think has been really exciting just to see how these deep learning techniques can just really solve meaningful questions. Outside kind of our core molecular machine learning strength. And with that, we shall punt back to another molecular machine. Oh, sorry, Vignesh, go ahead.
I think there was another question. Can you train?
Yes, please go
ahead. Sorry for interrupting. Yeah, the question is, can you train neural net? Can training the neural networks be much faster than solving the PDEs numerically, especially for higher dimensional systems? I think it is possible, and it also depends on your data source and your data set. Maybe if it's not incredibly large, I think you would be able to do it. And I also think it's not like maybe the better advantages would also be that not all the computational solvers are not maybe accurate. Maybe the PDE solvers could be more accurate. So it could be an interesting area of research to explore.
And to add maybe a little bit of color here, so we've had hints from Schrodinger's equation that deep learning is actually capable of solving extraordinarily high dimensional PDEs. So there's like the FermiNet paper and PolyNet papers from DeepMind and Frank Noe's group that solve these very high dimensional Schrodinger's equations. And I think we're just starting to see this really exciting new line of work where people are like, wait, you can actually do this for Navier-Stokes. You can do this for other classes of problems. And it looks like we have one more question from Inhi. Do you want to go ahead and answer that, Vignesh?
Yep. Actually, you can do the same thing with. That's true that NumPy is not scalable. And second, you kind of want those automatic differentiation operations. So you could either use an autodiff library, any autodiff library, but usually the traditional autodiff libraries are pretty slow. But JAX is kind of like an enhancement of the original autodiff library, and it has the speeds of TensorFlow and PyTorch. So yeah, that's true. We have used JAX for that, but you can also use TensorFlow or PyTorch. I mean, the original implementation is in TensorFlow as well. But the actual maybe the benefits of JAX could be that you could quite easily compute higher order derivatives by nesting functions. So I'll just do check out this link called the autodiff autodiff function in the JAX repository, where we've shown you where you can compute the gradients of the derivatives of functions such as the Hessian gradients and like even higher order functions for composing them. So yeah, that's the reason we chose JAX, but we could do it with other frameworks as well, but not with NumPy for sure.
Okay, awesome. Thank you, Vignesh. And I know this is like the Vignesh's work in the PD line of thinking is actually really exciting. So for folks, please keep asking questions in the chat section. We'll come back at the end, but I want to make sure our last speakers have time to present. So Seyone, Elana, Walid, do you want to go ahead and grab the screen there?
Can you all see my screen?
Yep, go for it.
Cool. I'm really excited to get to talk a little bit today alongside my collaborators about some of the work we've been using in establishing transformers as sort of a chemical foundation model. Next slide, please. So the main motivation of some of this work is molecular property prediction as a field has seen a recent surge of work thanks to the success of graph neural networks and graph convolutional neural networks on various benchmarks like MoleculeNet. But there's still a really big issue, which is data scarcity, where the number of labeled data sets that really exist that are high quality and high signal are really hard to come by. And so some of the motivation of this work is that given the availability of these huge unlabeled data sets composing of virtual libraries and chemical databases like Enamine, can we sort of try to use NLP architectures and self-supervised learning to try to learn on some of these unlabeled structural data sets and then sort of transfer that sort of prior representation towards labeled data sets, such as MoleculeNet. Next slide, please. But as a caveat, I think molecular transfer learning as a field is incredibly challenging, and there's been a lot of different sort of attempts to try to solve this problem, which is why I think it's sort of a grand challenge problem for the field. So if you look at earlier work from DeepChem, actually, they tried using image-based architectures like Conception. Sorry, could you go back one slide? Thanks. Yeah, so they tried using sort of image-based architectures like Conception, but results were really brittle. And other work from Stanford tried to sort of enable graph-based pre-training. And there's been a large amount of other attempts in multitask learning, low data drug discovery, one-shot learning, and contrastive learning. But there hasn't really been a very robust model that transfers not only on sort of these public benchmarks, but also on benchmarks and data sets in industry. And so we sort of wanted to answer the question of whether NLP techniques can do this effective transfer. Next slide, please. And so as a first attempt, what we wanted to try to do was adapt this task called mass language modeling for chemistry. So mass language modeling, or MLM, is a really popular task in the NLP field where, given an input string, you randomly mask, say, 15% of the tokens, or say 15% of the words, and you sort of have your model do this, basically accurately sort of demask or recover these tokens. And so this sort of enables you to use these non-labeled data sets and only use the actual string or language corpora itself. And we wanted to see if we could do this, but instead for predicting masked atoms or bonds. And another motivating factor for this work is that in graph-based pre-training attempts, like Grover, they actually do a similar task where they try to predict nodes or edges in a graph as a pre-training task. And now Elana is going to go more, sort of do a deeper dive into some of the pre-training tasks we built.
Yeah, so one thing we wanted to investigate was what is the best way to do molecular pre-training? And we've seen that when doing transfer learning with language models, typically improving pre-train loss can also improve the downstream fine-tune performance, but the degree of transfer can depend on the relevance of the pre-train task to the fine-tune task. So as I was saying, training a model to predict the missing atoms and bonds from a SMILE spring is one way to do molecular pre-training, but that may not be the pre-trained task that best leads to improved performance on the tasks we care about. So we wanted to actually evaluate and compare multiple kind of commonly used pre-trained tasks to see which is the most effective at transfer learning for chemistry. So to explain the task, we'll be using acronyms to refer to them. We have MLM, as I mentioned, masked language modeling, in which we mask out the characters and the smiles, and our model learns to predict these missing tokens, hopefully learning meaningful representations of the smile, since the smiles-based model doesn't necessarily have the most inductive bias about molecular structure in it. And then with MTR, multitask regression, we calculate a variety of RDKit properties that can be determined from the smiles, and then train the model to predict those. One thing to note is that this project is still a bit in flux, and not all of the MTR experiments are fully done running yet, so we'll be mostly presenting our conclusions so far. And some of the MLM MTR comparisons are not done yet. So here are some example properties for the multitask regression. We have about 200 total. Here you can see some of them. There's molecular weight, fraction of sp3 hybridized carbons, various electrostatic properties. One important thing to note about these is that none of these properties require chemical synthesis or testing in any assay. They can all just be calculated in RDKit, so we can scale this to any number of compounds we want, which is pretty cool. And here we have the flow of these pre-training experiments. So on the top row, we have the MLM pipeline. So before training, we have some randomly initialized weights, and then we used our masked smiles as our input with some self-supervised learning, and through predicting these masked tokens, we train the model until it converges, and we end up with the MLM pre-trained model. So if you recall from Ashwin's talk earlier, he referenced using the ChemBERTa pre-trained weights for his retrosynthesis task, and this is effectively the pre-trained model that he'd be referring to. But in our case, we now take this pre-trained model and fine-tune it on a variety of molecule net tasks and create a fine-tuned model for each of these tasks we care about. And then similarly for MTR in the row below, we start with our untrained model on the left. But this time we use both the smiles and also our collection of all the RDKit properties. So this data set is quite a bit larger. And instead of masking the tokens, we feed in a full smiles, and then we predict all of these RDKit properties to get our MTR pre-trained model, which we then fine-tune on all of the same molecule net data sets and create a separate corpus of the MTR fine-tuned models. Most of this project and this talk are focused on how to do pre-training well, more than just trying to get the best performance we can. But in doing this, we actually have incidentally gotten some pretty exciting results on various molecule net tasks that Seyone will talk about now.
Yeah, so across MoleculeNet, we evaluated on a host of different tasks across regression and classification. So for regression, we used root mean squared error, where a lower result is better. And on the other hand, we used RSC AUC for classification, where a higher score is typically a better performing model. So to start, we benchmarked against graph convolutional networks, which are kind of like the staple of molecular property prediction, as well as random forests on ECSP molecular fingerprints. And so we saw in regression, it was actually across all four tasks, across base, clearance, LiPo, and ESOL. ChemBERTa actually performed the best on root mean squared error. And for classification, where we evaluated on BBVP, ClinTox, Tox21, and the base classification test, we saw that it also, for two of the four tasks, that performed the best out of all the results, out of all the other models. And we're also working now to actually help do benchmarking on Grover, which is a new graph transformer architecture that I think has recently become state-of-the-art. So we're working on also enabling that. Next slide, please. I also wanted to add that DeepChem actually has a ChemBERTa code tutorial for people really interested in understanding how to sort of run different jobs with these models. So it sort of walks through how to do mass token prediction, how to actually visualize the attention weights of the model across different smile strings. And also it walks through exactly how attention is computed. And we also do, I think, an evaluation on the ClinTox data set. So we take a pre-trained MLM model and evaluate it on ClinTox, which is a classification task. Next slide, please. And also we make a lot of these pre-trained language models available in Hugging Face to sort of further open source development. So we have a lot of the MLM and I believe some of the MTR models, which are open source through DeepChem. So DeepChem actually has a Hugging Face organization that you can go to. And if you copy paste essentially the model path, you can actually use the Hugging Face model API to actually fetch these model weights and do anything you want with them. And I think really the motivation of this is not only to help enable molecular property prediction, like toxicity classification, protein ligand binding, and various other tasks, but we also want to see these models sort of touching back on chemical foundation models. We're also really excited to see them being adopted for other tasks, sort of like Ashwin's work with retrosynthesis. And now I'm going to hand it off to Walid, who's going to talk a little bit about hyperparameter search for pre-training.
Thanks. So yeah, now I guess we'll sort of start with how we actually got these models that were able to achieve these results on the downstream tasks. So sort of as a first pass, instead of sort of using the default parameters that are available, we wanted to do a little bit of a hyperparameter search to sort of have some confidence that we're actually finding the best type of ChemBERTa model that we can. And we wanted to sort of do this across this pre-training across a few different data set sizes. So we wanted to try to eventually do this on basically all of PubChem, but also to find the hyperparameters, we wanted to sort of use a proxy set. So for that, we're using the 5 million random subsample of PubChem. And we tried 50 different hyperparameter configurations. Of those 50, 38 of them successfully trained for a variety of reasons. So occasionally this might be things like, out of memory errors or sort of incompatible parameter combinations. But from those 38, we're also able to see kind of some insights into which hyperparameters seem to matter the most. So kind of on the right here, you'll see for both the MLM pre-training strategy and the MTR pre-training strategy, which parameters seem to be most related to or correlate the best with the eval loss. So interestingly, you kind of see that the log learning rate is actually positively correlated with the loss. So it sort of looks like the higher learning rate you have, the higher loss you have. And kind of conversely, the higher hidden size you have, sort of like the better you do on your loss. And one sort of interesting thing to note here is that we also plotted the number of parameters for the model, which is towards the middle of both of these plots. And you'll see that there's actually not a strong correlation with just the model size on its own, whereas it's actually that the parameters that sort of give you the overall number of parameters, like the hidden size and the number of attention heads, are actually what are most important. Next slide, please. And one thing to note here is that the correlation listed for learning rate especially is actually quite deceptive, because there's sort of these few data points at the high end of the learning rate spectrum that sort of throw off the correlations quite a bit. Whereas if you kind of look at the picture here, you can see that generally higher learning rates are actually more favorable for getting better eval losses up until a certain point, basically. So that was just one caveat that we wanted to note. And then these other two parameters that we saw in sort of that bar plot were the hidden size and the hidden size being basically like the most important parameter. And you can see here that kind of irrespective of the other parameters, it still does seem to correlate negatively with loss. So having a higher hidden size does tend to be better across most of these different model configurations. And this is just to give an idea of what this whole pre-training pipeline actually looked like. So again, we sort of did this hyperparameter search on the smaller set of PubChem, which was composed of 5 million different compounds. And then from those runs, we selected 10 configurations to try on a 10 million set. And then from those, select 5 configurations for the 77 million set. And the way that we selected those configurations was basically to pick runs that were across this loss spectrum. So we weren't always trying to pick out basically like the very best runs, although we have 1 or 2 runs that are towards the bottom there. But we wanted to really see if we could draw some sort of relationship between pre-training loss and eval loss, or sorry, downstream fine-tuning loss. And so that's why we were picking sort of across this loss spectrum, if that makes sense.
So yeah, kind of addressing some of the questions Walid was just posing. So because we ran these variety of experiments in which we kept the model architecture and hyperparameter fixed, and we only varied the number of compounds in a pre-training data set, so going from a 5 million sample to a 10 million sample to all 77 million PubChem compounds, we can actually evaluate how this pre-training data set size variable influences our pre-training loss. So on the plot on the left, we have 5 different model setups distributed across the x-axis and their pre-train loss on the y-axis. And each model was trained with various data set sizes, where the blue points represent models trained on 5 million compounds, green is 10 million compounds, and pink is 77. So we can see as we increase the data set size from blue to green to pink, the pre-train loss goes down, and this pattern holds across the various model setups. So that means that even once a model has seen 5 million compounds, it can still learn from seeing even more compounds, and iterating through that first set of 5 million compounds repeatedly until convergence will not lead to as good performance as a model that gets to see a new set of 5 million compounds after that first epoch, which is pretty interesting. And so then on the right, we can actually look at these trends to see, okay, going from 5 million to 10 million, there's still improvements, but where does this plateau? What does this plot look like? And so on the x-axis, we have data set size. The y-axis, again, we have the pre-trained loss. And the various lines are just the different model setups, so different numbers of layers, learning rate, et cetera. And we can see that there's a noticeable jump from 5 to 10 million, and then a relatively smaller one going to 77 million. And across the model setup, so the different lines, this pattern seems fairly consistent, although we can see that some models benefit more from the 10 to 77 million jump than others, like the green line, for example. With just 3 data set sizes, it's hard to fully predict what the relationship between data set size and pre-trained performance is, and know exactly where that fully saturated data set size exists. But it seems like these models might still benefit from increasing the data set size. And so, as I mentioned earlier, our MTR experiments are still running, and so these are only on the MLM, since MTR results, we only have finished through the 5 million so far, but hopefully soon we'll be able to see if MTR scales differently with data than MLM does. So we don't know that yet, but that'll be really interesting to find out, because it could be that MTR actually really benefits even more dramatically from going from 10 to 77 million, or maybe even less. And here we are looking at the experiments on just 5 million compounds, but we have the performance of MLM models on the x-axis, and then their corresponding MTR models on the y-axis. So each of the model configurations, we trained an MLM model, and we trained the exact same thing with an MTR model. So the models have the same setup, but different pre-trained task, different loss value. And it looks like there's a strong correlation between performance of various models trained on these 2 different tasks. So we haven't fully explored the implications of this yet, but it might imply that there's something fundamentally better about certain architectures and hyperparameters than others in terms of their ability to understand chemical space. And so now we're going to go a bit into the downstream fine-tune performance. So now that we've pre-trained a whole bunch of models, let's fine-tune each of those on molecule net tasks and see what we can learn. So we noticed in the previous slides that there are interesting patterns you can learn about how to improve our pre-trained loss for these various tasks, but do we actually care about optimizing our pre-trained loss? Does that actually help us transfer knowledge to the downstream tasks we care about? So over the course of training, as the pre-trained loss improves, we can take our model and freeze it as is, fine-tune that onto, in this case, a molecule net data set, and see how improving our pre-trained loss over time, over the course of training, affects our ability to then fine-tune on a chemistry task. So in each of these plots, we have our pre-trained loss on the x-axis, and on the y-axis, we have the Pearson R from fine-tuning on, in this case, the lipophilicity molecule net task. And we can see that over the course of training, as the loss goes down, as the plot goes to the left, our correlation goes up, which the higher the better, which is really cool because that means that over time, as we optimize our model for this pre-training task, our model is converging upon some representation of molecules that is increasingly more useful for being able to learn real complicated chemical properties. And this holds for both MLM and MTR. And then here we ran a similar experiment, but instead of taking models frozen over the course of training, we've selected a various collection of models, each from different pre-training runs. So they may have different learning rates, different number of attention heads, et cetera. And we want to see if optimizing our pre-train loss, not by training longer, but by changing our model architecture, can also improve the downstream fine-tune performance. And we see a similar story here, with the MTR having a bit of a cleaner trend than MLM, but fairly consistent. And I find this really exciting to see such a clean correlation given how messy these data sets can be. One thing I do want to be very careful on is overhyping these, because looking at these, it looks like there's a very clean correlation and there's still a lot of room for improvement, which I do think there is. But also this particular data set was cherry picked just because it seemed to have really good correlation between the pre-train loss and fine-tune loss. And so these patterns can actually be quite data set dependent. And I don't want to claim that these patterns are going to hold across all of our data sets ever. And as we'll see in the upcoming slides, this data set does have a bit better transfer learning ability than some of the other ones do. But Walid is about to go through those now. So I will pass it on to him.
Thanks. So as Elana mentioned, we were basically trying to now see what those pre-trained models look like when we start to fine-tune them on the downstream molecule net tasks. So in sort of the following few slides, there will be 2 slides at a time that basically give the same results for 2 data sets, but just in slightly different views. So in this view, we're grouping the runs together, the model configurations together by the data set size. So you'll see all the models that were trained on the 5 million set, and then the 10 million set, and 77 million as the groups on the x-axis, and each of the bars represents a specific model configuration. And so one sort of interesting thing here is that, as Elana showed a few slides back, as the data set size goes up, our pre-training loss does tend to go down, meaning that seeing more compounds is beneficial. So you'd expect to see some sort of trend across the data sets here, where we sort of get better and better. And on the left side, we have RMSE, and on the right side, we have Pearson R. And in both of these cases, we don't really see this pattern holding across the board, which is kind of a little bit unfortunate. It's a little bit sporadic and sort of mixed. So there's not basically a ton of conclusions we can draw from looking at this just on its own. And if you go to the next slide, we can see the same sort of results again, but now grouped by model configuration instead. So you see basically the model configuration specified by the run number on the x-axis, and now the color of each bar in those groups defines the number of compounds that we were training on. So it's the 5 million, 10 million, and 77 million set again. And something that you'd want to see in that, sorry, if you can just go back a quick second. Something that you'd again want to see here is basically within each of these groups, you want to see kind of either a decreasing or increasing set of bars based on if you're looking at the RMSE or Pearson R. But unfortunately, it's not clearly always the case. Next slide, please. And we kind of see a similar thing for the clearance and lipophilicity data sets, although the lipophilicity one, being the one that Elana was showing earlier as well with the scatter plot, does actually seem to have that sort of trend that we want. So you kind of see that things seem to get better as we go across data set sizes and in terms of runs where the pre-train loss is going up. Next slide, please. And again, looking at this by run, that's probably even a little bit clearer, especially if you look at sort of like the bottom right plot for the Pearson R with respect to the lipophilicity data set. With each of these model configurations, you're basically the best pre-trained model was run 45 in this case. That had the lowest eval loss, and you see that having the best Pearson R across all the different configurations. And you sort of see as you increase your eval loss, you sort of get worse and worse Pearson R. So that correlation does tend to hold for this data set, even though for some of the other ones it's a little bit mixed. And this is sort of just a refresher on the slide that we showed a little bit earlier, showing the actual results relative to the other 2 models that are currently in the molecule net leaderboard. So across all the regression tasks so far that have been evaluated, we have sort of the best results on all of those, which is very exciting. And so here we basically go into the same sort of analysis, but for the classification data sets. And so again, here these results are grouped by the data set size, colored by model configuration. And here it's kind of interesting where you see that basically one model configuration, run 45, seems to have the best performance for most of these. And that was the model with the very best eval loss. So while there isn't necessarily a super clear trend across all of them, it is kind of nice to see that the best model did essentially perform best on the downstream tasks as well. And yeah, we can go to the next slide as well. And so yeah, here again, we just look at the ClinTox and Tox21 data sets. Similar sort of results, although it's interesting to see that for Tox21, with respect to ROC AUC, we're basically kind of similar across a lot of the runs. When we look at PR AUC, there's a little bit more of a distinction amongst them. And again, sort of the lower eval loss data sets do tend to do a little bit better. Eval loss configurations tend to do a little bit better than the ones with the higher eval losses. Same view here again, just grouped by run instead of by data set size. And then we can go to the next slide, which is again a recap of the classification results, where we sort of have a little bit more of a mixed bag by looking just at ROC AUC, but we're still at least competitive on the ones where ChemBERTa is not the best. And at least for BP so far, we're beating out the other models that are in the leaderboard so far.
And yeah, so this is still a work in progress, but the next steps, some of which we're actually working on, others are in the future, are just to finish running the MTR experiments so that we can do a bit of a more thorough MTR versus MLM pre-training analysis, and also do comparisons to other state-of-the-art architectures such as Grover, and then scale up our pre-training dataset size and see what is the actual limit of at what point have we made use of all the possible data we can for these models, and even just evaluating on other downstream fine-tune tasks to see are there specific areas where transfer works better or worse based on the pre-training task. Yeah, so thanks very much for listening. Now we can probably take any questions people have. I saw some popped up in the chat.
Okay, awesome. Thank you all. And I think with that, we can kind of transition over to questions and discussion. So, feel free to ask questions. We'll start with the ChemBERTa questions first, but we can then kind of move on to general questions for any of our speakers. And I'm going to ask a bit of a plant question because I'm obviously working on ChemBERTa as well. But would any of you be able to comment on how you see ChemBERTa performing with respect to other methods like Grover or the SNAP Stanford pre-training methodology?
Yeah, so there's like a lot of correlations between the MLM task and some of the pre-training that SNAP's doing. For reference, the SNAP group, if I'm correct, is doing a lot of various masked-based graph pre-training for small molecules. I don't think they've done the same level of like intense evaluation with data set size and optimizing the hyperparameters for this. But I mean, theoretically, they might have quite similar performance. Granted, graphs have a bit more bias about molecular structure than the SMILES-based method does. So I assume that in smaller data regimes, it might perform better, but I don't know how it will scale differently. Does anyone know if they've done like really large scale benchmarking? It would be interesting to see the comparison on those.
I think to add in just from what I can see, I think Grover has done probably the largest benchmarking of a graph-based pre-training style I know of. And I'll try to drop the link to the Grover paper here in the chat. One issue with the paper is it's a little difficult to do apples to apples comparison of some of the numbers because they've used somewhat different methodology for doing benchmark numbers. So this is part of the reason we are doing a benchmarking effort as part of this new molecule net2 paper to be able to answer some of these benchmarking questions. But I'm not actually sure if the Stanford's folks have done large-scale benchmarks of the graph-based pre-training.
Yeah, one thing that's hard to compare them is kind of, as you mentioned, a lot of groups use different like splits for some of their evaluations. And so it can be hard to do as you said, the apples to apples comparison, because I can see like how their model performs across their particular split compared to other models. It can be hard to then transfer that to a different paper that uses a different split.
Yeah, the other thing to note is that at least for the benchmarks that we've done so far, for the MoleculeNet leaderboard, I don't think that the GraphNet there was necessarily a pre-trained model. So it would be interesting to see that those results kind of, if we can get an apples to apples comparison with the Grover architecture, that would be interesting. And then also sort of some of the pre-trained models that came out of that strategies for pre-training graph neural networks paper from the Pandey group a little while back. I think those would probably be sort of a more fair comparison to be comparing ChemBERTa against.
Yeah, so I have I think a very related question, which is just, I guess, thinking about chemical foundation models and representation choice more in general. Do you think that, kind of from the scaling that you've seen, if you extrapolate forward, is a string-based representation like SMILES going to be good enough in the appropriate data regime to kind of get you to where you want to be for a chemical foundation model? Or, are adjacency matrices or even something that includes 3D information, is kind of a different sort of representation going to be needed at some point?
Yeah, I think that's a great question. And one that I guess I have some initial thoughts. although obviously I don't know the end answer. I mean, it is sort of tempting to use one of those architectures because of sort of like the better representation that you get, like you said, of 3D information and graph structure natively. But it is also interesting to see if we can sort of achieve some of that with the language-based models, which is appealing for a couple of different reasons. One of which is just that there's a lot of sort of pre-built infrastructure for training these models at scale, particularly through Hugging Face, which we've been making use of. So to some extent, it's kind of easier to scale this from a computational perspective than it might be sort of graph-based models. Another thing that we haven't really encoded too much, although I know that in a previous iteration we did some evaluation of this, but trying to play with the type of tokenizer that we use and being really sort of encoding some inductive bias there about the types of groups that we want to basically partition out by using that type of tokenizer. I think that might be a way to sort of encode some of that similar information and sort of let these get competitive with enough data. But I guess to be seen.
Cool, thanks.
Yeah, I think just to add on, like I think intuitively, like a 2D like network graph probably does a better job, like for a model to learn on. But I think what we're trying to see is, can we, since NLP offers a lot more scale, can we sort of outscale graph-based pre-training methods and try to see if that can sort of compensate for the fact that it isn't able to as easy, it's not, say, as strong of a representation. So it's kind of comparing the scale versus sort of the representation is sort of the question.
All right. So if anyone else has questions, just feel free to hop in. I think that let's say we can have like 5-10 more minutes of questions before we start wrapping up. And maybe as a question directed at Vignesh. So for your work on PDEs, like, do you think that there's any, do you see kind of like, what are some of the extensions that you think that you can make to your current existing API and infrastructure?
Okay, one sec. Sorry, 1 second. Sorry for that. So the thing what I think is that either first I want, like I already discussed, I want to kind of thinking about improving the kind of like the UI UX so that it's kind of easier for users to solve a differential equation directly using a sort of like a latex differential equation code, so that sort of so you don't have to write all the backend code as much. Just you could either work on just simply writing that part, and you can easily solve differential equation. That would be a lot smoother. The other thing which we've thought about is that currently the pin API kind of expects the user to kind of enter the sort of like I had explained in mine, that there are two different losses for the PD. One is the differential loss and the other is the supervised loss. So it's sort of like the users kind of adding the supervised loss. So sort of like we're thinking of ways to separate those two things out, so that the user just has to include those functions as two separate things, and we could do the gradients, the computing the gradients at the backend. So we're kind of thinking of ways to do that. And the other, for now, these are the ways we're thinking of improving the PD API. I mean the pins API in DeepChem.
Okay, awesome. Thank you, Vignesh. And maybe just as like a question for Atreya. So for the matrix attention transformers, like, what do you see as kind of the next steps for like the model? Are there kind of ways you think you can extend it directly, or perhaps like actually maybe as a more general question, how do matrix attention transformers compare with Hugging Face style transformers?
I'm not actually very familiar with Hugging Face style transformers, so if you don't mind, I'll get back to you with that after going over Hugging Face a bit more.
I think that works just fine. Right. Any questions from the audience? Kind of last call, I think, before we start wrapping up. So if you want to talk to any of our speakers, now's kind of your chance. Okay, going once, going twice. All right. So I'll just kind of end on a few logistical notes. So thank you all for attending our first online DeepChem meetup. I hope we'll be able to have another one of these in a few months down the road. As a community, DeepChem, we are always looking for new contributors. Maintaining a large open source package is, as you can probably imagine, a whole lot of work, and we need help. We definitely need help, especially on new contributors to contribute new scientific models, but in particular, like seasoned engineers who can help us do things like maintain the correctness of our test suite, maintain our infrastructure for CI, CD, and to help us manage releases. So if you're a seasoned engineer who liked our some of our talks today, please consider contributing your time to DeepChem. We can definitely use your help. For the students who are listening, we hope you've kind of learned something. DeepChem is open to any students who want to participate. We have open weekly calls and we have open office hours. We've had a number of research papers, like for example, the last talk was a research paper written by the lead author, Seyone, actually when he was in high school. So we've had a number of younger researchers get involved. So part of our goals as a community are to facilitate research from anyone across the world. So the only bar is, of course, getting involved and doing the hard work of learning. So thank you again, everyone, for dialing in. We will have probably another event in a few months. Follow the DeepChem organization on Twitter, sign up for our forums, or sign up for the meetup group, and you'll be able to stay in the loop. And I wish you all a wonderful rest of your Wednesday. Thank you again, everyone.
Oh, thank everyone so much. Thanks for making my morning, everybody.
Yeah, thank you for this.
Thanks, everyone. Bye.
Thank you. Thanks a lot for this.